package of Avalon cigarettes, please.
Yes, sir. Oh, just a moment, sir. And don't forget your change. You never guessed, but Avalon's cost you less.
So why not always travel on with Avalon?
Good evening, friends. Good evening. This is Del King.
Hello, Randy, K7AGE. I'm at the WLW station. So we're going to take a little tour inside this building, and we're going to kind of go back in time. Back in 1932, this station went from 50,000 watts to 500,000 watts. It was the only AM commercial radio station ever to go to 500,000 watts.
Welcome to WLW. My name is Jay, K8CJY. This is Jeff, W8GNM. We're both ex full-time Harris people, now part-time Harris people. Ted Ryan, Ted's the chief engineer for WLW. And Ted Kendrick is a retiree from this location.
One of the station engineers for this facility, yeah.
So a little bit of history. WLW went on the air in 1921. Started out as a 5-watt station in Powell Crosley's living room. The next move was to the factory for Crosley Manufacturing, which originally was a manufacturer of automobile accessories, and went to 50 watts, and then later to 500 watts using homemade transmitters. Ultimately, they went out to a place called Harrison, Ohio, which is far to the west of Cincinnati, with 5 kilowatts. And there was another station that went on the air in around 1922 that was put on the air by the U.S. Playing Card Company, and its call letters were WSAI, Standard Amusement Incorporated, which was the parent for U.S. Playing Card Company. WSAI's purpose when it went on the air was to teach people to play bridge. And they played around with that for a few years and finally got kind of tired of it. And Crosley, sort of in the mode of an LMA, ran it for a while and then ultimately bought it. But while it was owned by the U.S. Playing Card Company, they moved the transmitter from the plant in Norwood out here to this piece of property in Mason, Ohio, built this building over here, which is now where Ted and his wife live, and put a Western Electric 5 kilowatt transmitter in that building. And out here in the lawn and behind it were 2 towers that supported a flat top antenna, with the house kind of right in the center of the flat top antenna. And for 3 years, WLW operated from the site in Harrison, Ohio. And Powell Crosley always did things in 10 dB increments. He always wanted to grow in 10 dB increments. So he was at 5 kilowatts, and the next increment was 50 kilowatts. And he realized he couldn't do it down in Harrison, so he bought WSAI and came out here with WLW by building this building, the front half of this building, and over in the field over here put up a tower and another one in the back, with the white building out there as the center point between those 2 towers, and put another flat top up, and bought a Western Electric Model 7C transmitter, which we're going to see the sort of the pieces of. And actually the building out here is built out of the white building is built out of the packing crates that the transmitter was shipped in. We've actually verified that. We went out, pulled the ceiling tiles down, and the Western Electric stamps are on the wood. Okay? So they installed the 50 kilowatt transmitter out here. WLW was one of the first 50 kilowatt stations, but Powell wasn't satisfied with 50 kilowatts, so that happened in 1928, and he began thinking about the next 10 dB and what it would take. And at the same time, vertical radiators were coming along and people were getting away from flat tops. So he contracted with Blah & Knox and built what was originally an 831-foot vertical radiator. It was 831 because there was a mast a lot taller than the one on top that was on the tower. The idea was build an antenna that could handle 500 kilowatts. And they then went to RCA, who was not in the transmitter business at that point in time. RCA was more of a project manager, and RCA took on the job of designing and building the 500 kilowatt amplifier. Not a transmitter, but an amplifier, because it was a power supply, a modulator, and an RF deck that was driven off the 50 kilowatt Western Electric transmitter. Contracted for in 1932, delivered in the winter of 33, and first put on the air in the spring of 34. And to do that, they had to build a building essentially around the transmitter components. So they added a rear section to this building, and the transmitter basically takes up from east to west on the building. Most of the magnetics were out back on a pad. There's still part of them out there. The modulation transformers were in the basement, along with the filter capacitors, and you'll see pictures, not tonight, but there are pictures around of the original filament and bias supplies, which were large rotary converters, motor generator sets, to develop the thousands of amps of DC necessary to light the tube filaments in the transmitter. So WLW went 500 kilowatts. They were on the air a short period of time, and a grievance was filed by the Canadian government because they were obliterating a station on, I think, on 690 up in Toronto, near Toronto. And Crosley had a lot of smart engineers, so they got together and developed a pair of vertical suppressor towers, which were actively fed by sampling part of the transmission line power, routing it out on open wire, and the two suppressor towers were across the street on property that was also owned by Crosley and known as Everybody's Farm. Everybody's Farm was an experimental farm that Crosley used and actually gave agricultural reports throughout the day, market reports, as well as instructing farmers how to fertilize, how to plow, how to plant, etc. And there was a studio across the way, and they put the suppressor towers up over there, and they were able to reduce the signal level in Niagara Falls, New York, at 500 kilowatts to the same level it would have been at 50 kilowatts without the suppressor towers. So that enabled them to continue operation at 500 kilowatts. They went back on the air in the fall of 34 and continued to operate until 1939, but they operated on a special temporary authority, so they didn't have a full-time license. Every 6 months they had to go to Congress and the Federal Radio Commission, and later the FCC, and renew the authority to operate at 500 kilowatts. And eventually they were challenged because they were actually operating with one station and covering as much as the networks were covering with groups of stations all around the country. And many entertainers got their start here in Cincinnati. People like Red Skelton, Red Barber, who was a famous sportscaster, a number of other folks performed on WLW from the studios, which at that time were in the Crosley Manufacturing Building down in Spring Grove Avenue.
So you are looking at the remnants of the 500 kilowatt Crosley transmitters. Jay mentioned this transmitter was designed and built in the early 30s, 1932, 1933 era. RCA Victor Corporation was the program manager, and they get to put their name on it and take credit for it. But it was actually built by a team of companies and individuals. The RF power amplifiers, and I'll say more about those. Those are these three cabinets over here. Were designed by engineers from General Electric. The audio section, which is right behind me, the power supply rectifiers are at the far end. This section here, which is the modulator and the transformer and the magnetics, were designed by Westinghouse in Pittsburgh, Pennsylvania. The magnetics were designed and manufactured in Pittsburgh. So it was a joint effort. I did a little bit of research on this a number of years ago and looked at the team members, and I came to the conclusion that the average age of the engineers that developed this transmitter, remember, there's nothing like this has ever been done before. This is really groundbreaking. The average age of these guys, and they were all guys, I'm sorry to say. Today we'd have ladies involved. They were 27 years old average age. So this transmitter was, as I like to say, and Dave Hirschberger will understand this very well, this is designed by a bunch of space cadets, right? Right? So they did have a couple of old salts to help them along the way and guide them and mentor them a little bit, but it was a very young team of engineers. You can imagine how excited these people were to be working on a project like this and really breaking some ground. Jay is leaning on one of the 892, is that the 892 or the subsequent one? That's the three-phase filament one. So 862, well, this thing had a lot of water-cooled triodes. This is the water jacket to cool them. Did you point out the cooling pond outside? I don't know if you noticed that thing looks like a vacant or dead swimming pool. Yeah, that swimming pool out there, that's a cooling pond. They used evaporation cooling to chill the water for the transmitter. There are 4 tubes in each of the 3 amplifiers. Each of these 3 amplifiers could generate about 180 kilowatts of power, and they were seriesed. And then the modulators had more pairs of these 862 or 892 tubes. Now, the original tubes had to have DC on the filaments. If you didn't have DC on the filaments, you'd get modulation in the tube. As the voltage varied across the filament with a 60-cycle rate, it would modulate the emission of the tube and introduce hum and noise on the carrier. So they had to use motor generators. So they had AC motors in the basement driving DC generators. And as Jay said, there were thousands of amperes of DC power being generated to light the filaments.
1,500 amp DC motor generators.
Later on, if you look at this, this is a little more complex. This has 6 pins. They're 3-phase filaments. So there's actually 3 filaments in there, and they were organized so they could put polyphase AC power on them and have humbucking in the filaments themselves, so they didn't have to have DC power to operate the filaments anymore. When you go by here a little later, we're going to walk around in a minute. We're going to go behind the transmitter, and I'm going to open some doors to show you the back of the power amplifier. But you'll see a lot of Pyrex tubing here. There was about 12,000 volts DC on these tubes, so the water that was touching them and flowing over them to cool them had to be distilled water, had to be very pure, and there had to be a long creepage or insulator path in the form of Pyrex tubing or spiral wound ceramics to get the voltage from ground potential up to 12,000 volts and back safely. The power amplifiers, when we look at the construction of them, they were push-pull amplifiers. When you go around back, you'll see the tank circuit. So anyway, let's see, what else can we say?
I assume that when this transmitter was on the air, it took a team of engineers watching it all the time.
About 13 engineers.
Yeah.
And the startup process was several hours because they had to bring tubes up to temperature. We have a friend who's 90 years old, Clyde Hangley, who's the former VP of Engineering at Avco Broadcasting. Clyde started here as a co-op student from the University of Cincinnati And his job on with the startup of the 500, by the way, the 500 ran until 1943 on a temporary basis overnight, only from midnight till 6 in the morning.
During the experimental period.
And it was operated under the call W8XO, not WLW. But Clyde's job was to come up and crawl into the individual cabinets, no high voltage, only filaments on, put welding goggles on, and look down into the tubes, individual tubes, to see if anything had moved physically that would cause a filament to grid or a grid to anode short before they started applying high voltage. And he had 12 tubes to cover in the RF deck and another 8 tubes to cover in the modulator. That's part of the startup process.
Starting up this.
How often he found such a problem?
I have no idea.
Yeah.
You can ask him.
Actually, yeah, he was going to try and be here this evening, but for whatever reason, he didn't make it.
You might want to talk about the switching, because there are 3 PAs, 2 modulators, and all of this could be isolated. There's a very unique switching system. Jeff?
Yeah. Well, just to finish up with what Jay was saying, starting up this transmitter was a little bit like a shuttle launch. So there's a large crew of people, and there were a lot of steps and checklists and things to bring this transmitter up. So I think what Jay was referring to, and we're going to see some more of these parts as we walk around behind, and then we're going to go down to the basement and see one of the original modulation transformers. But these 3 power amplifiers were actually connected in series, and you'll see a sliding switch that's just under the floor here that could be used to put all of the amplifiers online, or any combination of them online. The coax you saw running out to the tower there, that big cylindrical lumen, that's the original 100 ohm coaxial line that was homebrew, basically. 10 inch, yeah, it's about 10 inches in diameter. They use heliacs now, 3-inch heliacs for the 50 kilowatt. There were 2 modulators. And there were 2 separate modulation transformers, so they were completely independent, and they could route those. They could run them in parallel, or they could route them individually to a single amplifier or pairs of amplifiers. The modulator was capable of about 180 kilowatts of RMS power. Per modulator, yeah. So it'd be 360. So it takes roughly 50% of the carrier power to 100% modulate transmitter. So
I recently read an article on when they were bringing the transmitter up and the testing they did. And according to the article, at one point in time in the testing, they actually had the thing up to 800 kilowatts carrier. So there was a lot of over-design.
Just to give you an order of magnitude here, this is driven, the driver is a 50 kilowatt transmitter in the next room, the Western Electric. So, you know, this is on 1 amplifier. This is the grid amp meter. So it goes to 10 amperes of grid current, right? And this is an RF amp meter. Notice it's a nonlinear scale. So this is a thermocouple General Electric RF amp meter. This is the plate tank circuit amp meter. It's 160 amperes full scale for 1 amplifier, right?
The power supply, 12 kilovolts, shows that the power supply can operate at 100 amps. So 1.2 megawatts of DC.
So those are the 3 RF power amplifiers. These are the modulator sockets. So for each of the modulators had 4 tubes in parallel push-pull. And you can see the tubes are still in the water jackets here. This is another one. I think the tubes have been removed. Now there's 3 tubes left. 2 of them are still in the sockets, and the 3rd one there. Here's a piece of the Pyrex pipe, piece that got broken, but you'll see a lot of it, and you see a lot of other Pyrex fittings here that were used to carry the distilled water in and out of the tubes. Now, the original rectifiers were glass mercury vapor rectifiers. They were later replaced with metal mercury vapor rectifiers, but you can still see them here. So this is a polyphase, 3-phase rectifier with 6 rectifier elements in it, okay? So these are actually mercury vapor rectifier tubes that were used to rectify the high voltage AC to DC. The filter capacitor banks were in the basement, and you'll see those in a little bit. This is the Faraday shield here. You can see the rods that are all connected back to ground and open circuited at this end. This inductor back here, my hand is, that is the plate inductor. This piece here, you see this piece that rotates? That's the variometer. It can rotate all the way around in the other direction. So this is what's used to tune the amplifier. You can see the two, what we call bread rack assemblies. These are the, again, if I had should have brought a flashlight with me, but yeah, there you go. Great. All right, so thank you. So here you can see, this is one of the bread racks. You can see the alternating plates, so it's just like an fixed air capacitor. And the other one is over here. And the two top sections here are then connected to the two pairs of tubes. That's one of the plate chokes to get the DC onto the lines here. You can see all the attention to detail on the corona rings here for high voltages. This push rod here moves this section. This is the output coupling inductor. This moves back and forth, so it comes out this direction or moves back in closer to change the output loading of the transmitter. And the output from the transmitter are these two 3/4 inch copper pipes that go down into the switching mechanism underneath the floor there.
And how is the variometer tuned?
From the front panel, see this gearbox here? Yeah, so you just dip the plate current, and peak the output, and you see the flexible couplings here, and the gearbox, and see the insulated section here, okay? Corona ring there, and this is a rotary joint. So this one turn that I'm shining the light on right here is the one that turns, and there's a sliding contact, a rotary joint right there, and another one at the top. So we've actually disconnected these things and measured their inductance and measured the inductance ratio because we wanted to learn about, we were trying to build a 250 kilowatt variometer for a modern transmitter and trying to learn about how this one worked. Yeah.
So this is the part of the building that was added on when the 500 kilowatt was built, and there's, again, remnants of the 500 down here. When the 500 was built, there was a substation that was built out on Tylersville Road. Right now, there's nothing left but the weatherheads where the cables come out of the ground. But there were huge transformers, disconnect circuit breakers, and two feeds. One came from the Port Union substation, the other came from the Oakley substation, and came up, and they could select power from either of the two substations, the feeds into the plant. 33 kilovolts primary power, stepped down to 2400 volts, and the 2400 volts, and there were dual feeders, came into the building right here on cable A and cable B, and from there, the power was routed over here to these oil breakers, which had the ability to cut the power in literally a cycle or two of the AC sine wave. And that then fed AC back out to the plate transformers, which were on the pad behind the building. So there are a number of breakers, and then there's control power over here, which was used to feed the control circuits of the transmitter. And this back part of the room was all filled with the rotary converters. Later on, the rotary converters were transferred over to filament transformers and power supplies, which were on a pair of I-beams that spanned the building. And the holes that you see in the ceiling were where the filament wires went up to the tube sockets. And that was all torn out sometime, I guess, in the 70s or 80s. So anyway, there's also a harmonic filter and changeover back here, which you can take a look at. And then the switching system that Jeff talked about is this large ductwork that runs underneath the amplifiers. And all of that contained the high voltage, the RF, and other control circuits that were part of isolating each of the amplifiers.
So while we're standing here, this is one of the two modulation transformers. So it doesn't look like exactly like what we hams think of a modulation transformer being some laminated transformer. It's a big tank of oil with a transformer immersed in it, so it's like a giant pole pig. I'll read you the specifications here from this. Okay, so this was built by Westinghouse Electric in Pittsburgh. It's 180 kilovolt ampere capability, operated at 6,365 volts. It's rated from 30 cycles to 10,000 cycles audio frequency response. It has 725 gallons of oil in it. So the approximate weight of the transformer itself, the magnetics of this one by itself is 27,000 pounds of steel, iron in it. The case is 3,250 pounds. The oil is 5,460 pounds. Its total weight is 35,700 pounds for this, okay? The high voltage input was rated up to 14,400 volts. So this was one of two modulation transformers. I often wonder what it would have been like to stand beside one of these while it was modulating, whether you'd hear anything. You know, we're used to hearing a non-oil immersed transformer kind of talk, the magnetostriction of the laminations pulling them, being squeezed together and expanded as the current goes through the transformer. So you kind of hear audio coming up. I don't know whether this is all muted or glug, glug, glug in oil, but it would have been interesting to stand beside this thing when it was putting out 180,000 watts RMS audio power. That is a big audio amplifier. And there were two of them here. The other one was standing right beside it. So pretty impressive. The modulation reactor was out on the back pad. So the audio from this transformer was AC coupled to the power amplifier. And the DC feed to the amplifier was through another device almost as big as this called a modulation reactor, which was just a large high inductance choke that was used to feed the DC to the power amplifier tubes and offered a high reactance to the audio so the audio could go across it. But they didn't want to put DC through the secondary of this transformer because it would saturate it and it would compromise the performance of it. So, yeah.
One other thing I can point out, if you notice over here, what looks like a footer is actually a platform, and when the 500 was there were banks of Pyranol, GE Pyranol capacitors that made up the filter for the 12,000 volt power supply, and there was a series of caps that were used to isolate the DC, block the DC off the winding on the secondary of the windings off the secondary of the two transformers. So the coupling cap for the audio and the filter caps for the power supply were all out in the open. You can imagine having something like this today in the world of OSHA. Yeah. Right?
Well, this room was interlocked. It had to be interlocked. You know, it would be a death chamber. This is a bank of air capacitors, and I believe this was originally out at the antenna tuning unit. Okay, so these are cylindrical coaxial air capacitors. Okay, so they're just air gap space and they're in parallel. So there's 6 of them in parallel to form a high voltage capacitor. And there's also a lighting choke here for AC, decoupling the AC lighting from the tower. There's what's called an Austin ring transformer out there now. The part of the original harmonic filters over here, so you can take a look at the stack of capacitors they have. These are mica capacitors that are in series and in parallel to form one of the capacitive elements in the harmonic filter. And here's an antenna line switch. It says it's a switch between 50 kilowatts and 500 kilowatts, so it must have been between the two transmitters. So
this originally sat over there right underneath that
okay.
coax.
Okay. So if you look up here, this is the coaxial switching arrangement, and this is beneath the power amplifiers. So you see there are 3 different transmission lines from 3 different amplifiers here that had a sliding switching arrangement so they could connect them in series or take some of them offline and leave the others online. So, and then the output line to the antenna system was right here. So this is the RF switching network, all homebrew, as we should say, you know.
Friends, we cordially invite you Saturday evening at this same time when the Brown and Williamson Tobacco Corporation will again present Avalon Time. This is Del King saying good night, everybody. Avalon Time originated in the studios of the Nation Station and has reached you through the National Broadcasting Company.